Hello everyone, welcome back to Introduction to Semiconductor Devices. In the last lecture, we were talking about PN junctions. We talked about how these are fabricated and how the basic electrostatics of PN junctions can be understood. So quick recap. So essentially when you have a P-type and an N-type semiconductors, they're in contact, so because of the concentration gradients of holes and electrons respectively, there will be a diffusion of these holes and electrons, which will leave behind a positively charged space charge region in the N-type semiconductor and a negatively charged space charge in the P-type semiconductor, right? And then we drew these profiles, essentially charge profiles. For example, here, charge as a function of x. We said that there is a positive charge, and this is uniform here because this is coming from the uniform doping of the semiconductor, right? And we labeled the edge of the depletion region as xn, and on the other side we called it xp. So based on that charge, we applied Gauss law. We said d by dx is equal to rho by epsilon silicon, and then we solved for it. We said that the electric field has to be a linear function, and then we presented various arguments and then finally concluded that the electric field has to be in the negative direction and it has to show a triangular profile like this, all right? And potentially simply the integral of the electric field. So from that we showed that the potential should be a quadratic form, all right? So a few important things that I want you to note. The first one is that the product of the charge density times the depletion width is constant. For example, here in the acceptor region, the P-type region, acceptor ion concentration multiplied by xp, that is the edge of the depletion width, will give you nd times xn. This is simply charge neutrality if you look at it, right? Because you are not having any initial charge, right? So when the holes and the electrons diffuse, what they leave behind should be equal to the total amount of charge should be equal. Okay, so it's essentially the area here on the P side should be equal to the area on the N side. Okay, and we also derived expressions for electric field and potential. So I would like you to not memorize these expressions, but remember how they're derived all the time. Okay. So once you know that the charge density is, d by dx is proportional to charge density, you could immediately integrate and know that it's a linear function, right? And why it is negative direction, why is there a peak at x equal to 0, and so on. You have to please analyze it and understand it from the intuitive, qualitative way. Then the math automatically falls into place. Okay. Otherwise, you would memorize equations, and there's always a chance of making a mistake. Okay. All right. So, and then we derived an expression for built-in potential. I said that this is not a very common form, but yeah, this is just telling you that the potential is going to be quadratic function of x, right? Okay, so today what we would like to do is draw the band diagram of a PN junction. Okay. So as I've been telling you, band diagrams are very, very useful tools because they give you a lot of information in a very concise manner. So to do that, let's take a semiconductor this way. So basically, we have a P-type region and we have an N-type region here, right? There are these two semiconductors. So they have the corresponding doping. So I have not drawn EI, but there should be an EI here and there should be an EI here, right? So this distance is going to be EF minus EI, right? This is EF minus EI. I'll simply denote it by, I'll call it Q times phi Fn. Okay. So basically I want to talk of potential. So I just put in phi. This potential is referring, and then Q is charge, right? So basically the charge time potential should be energy. So I'm just saying that this is N-type region. And similarly, for P-type region, you should have, this is EI minus EF. And I'll simply call it as Q times phi Fp. So essentially the distance of Fermi level in volts, okay? Phi is that, okay? All right. So we have this is a regular semiconductor, right? So now how do we draw a band diagram? Well, these are in contact, they are not separate, right? So when they come in contact, we have mentioned that under equilibrium across a semiconductor, the Fermi level has to be constant. Right? There is no other electric field applied. Right? It's just under equilibrium. So the Fermi level has to be constant. This we have seen a couple of times already. So let's start with that. Okay. So basically, I'll draw a Fermi level all across the device, and I'll say this is EF. Okay. So I'll also list the steps in drawing a band diagram. Okay. Steps in drawing a band diagram. So any band diagram, you need to follow this. So this is the easy way for you to draw them without any difficulty. So the first one is draw EF at equilibrium. Okay, so we know that this is uniform across P and N regions at equilibrium, right? This is what it is. All right, so we have done this. Then draw the EC. Let's see. Draw EC and EV quasi-neutral regions. Okay. So we said quasi-neutral regions are those regions which are away from the junction, right? So on the N side, what should be there? We should have right. So it's an N-type semiconductor. So the Fermi level is closer to EC, right? So I'll just put that here. So I'll draw a Fermi level, which is EC here. And then I'll maintain a band gap and I'll draw EV. Okay. So this is a Fermi level for the N-type semiconductor. Similarly, I can draw the Fermi level, EC and EV for the P-type semiconductor. So P-type semiconductor, the Fermi level has to be close to the valence band, right? So here I would put in EV, and then approximately I will draw the EC. All right. So this is how the equilibrium band should look like in the quasi-neutral regions. So what happens in the depletion region, right? So we said that, depletion region, essentially there's an electric field, right? And you remember we said that electric field is basically 1 over Q DEC by dx, or you could write it as DEI by dx or DEV by dx. So essentially electric field is always a gradient in the electric field. And we know that in the depletion region, there is an electric field in the negative direction. So there's going to be a decrease in EC. Okay. And that also seems natural given that, your field is not going to do anything to the bands, right? So the bands have to be maintained the same distance, right? Band gap has to be maintained. Band gap is not going to change just because we apply an electric field, right? So basically the third step in your recipe is connect EC and EV in P and N regions, maintaining EG. You can't change EG, right? Because it's a material property. And just because we just put them in contact, that cannot change. Unless the lattice structure changes, EG is not going to change. Okay. So that's it. You have your band diagram. Okay. So after that, essentially, you can also put in EI. Since I have not done, EI is going to be exactly in between EC and EV. So this is going to be EI. Okay. So this is your band diagram. Okay. And a slightly neater version is actually shown here. Okay. The same diagram, just done. So what can we learn from the band diagram? Okay. The things we can learn is, of course, if you look at regions, if you let's say 1 and 2, all right? So basically, let me call it 1. Why to call it 2? Okay. 1, region 1 and region 1 here. So basically, 1 is a quasi-neutral region. Region E is equal to 0 because there is no gradient, right? Because no gradient in EC or EC or EV or EI, right? So in region 2, if I put it, so in the depletion region, you have a electric field negative, okay, because as you are going to minus x, field is increasing, so electric field will be negative. Okay, what else? Well, I mean, if you look at, remember what we said about the energy, right? So if you go towards the higher side, in the upper side, so this is essentially electron energy. Electron energy. So electron energy increases as you go towards, into the higher energies. And similarly, if you go towards lower energies, so this is increasing Hall energy. Okay. So now what is this telling us? Suppose let's say I'll put this as 3. Okay. 3 is basically electrons in n-type semiconductor, right? N-type semiconductor. I'll say n-type region. So they are at the lower energy. Can they go into the region 4? I'll put a region 4 here just to indicate. Okay. Electrons in the n-type, can they go into? Can they move into region 4? Well, they cannot, because region 4 is at a higher energy. And we know that typically all carriers would like to be at the lowest energy, right? So they have to be in the lower energy, so that won't happen. Similarly, in region 4, if you look at the whole energy, right, this is, yeah. So region 4 holes in region 4, or holes in p-type semiconductor, p-type region, have lower energy than n-type. So holes would like to stay in the p-type region. So essentially what you're having is an energy barrier, right? So basically both electrons and holes are seeing a barrier, energy barrier. They're not able to go into the higher energy regions. Okay. And you could also talk of potential, right? Potential seen by a hole, right? Fifth one, potential seen by a hole. How much is that? What is the potential that will be? So essentially you have potential energy, and then you have basically potential energy is charge times the potential, right? So for a hole, the charge is Q plus Q. So essentially it will be the same. So as you go from left to right, let's say this is increasing X, and you follow a hole. So what's happening? Holes in, let's say, this region, right? Let's say this is a hole in the p-type region. Okay, I should not put it. Okay, yeah. Well, yeah, hole in a p-type region. So as you travel across the junction, it is seeing a energy barrier. So that essentially it is seeing a potential which is in this fashion. Okay. And this height of this potential is what we call as dBi, built-in potential. Okay. So this is how we can understand. This is the information that we can get so far from the band diagram. Of course, we also know how much is the carrier concentrations, right? If you know these numbers, how much is this distance in energy, we can even calculate carrier concentrations. We can calculate built-in potential. Everything we can do just by looking at the structure, band diagram. Okay. So let me try to tell a little bit more. Okay. Let's see. So now let's look at it one more time. This potential, this band diagram. What is the carrier concentration? Okay. Let me see. So essentially, let's consider this is vertical axis and horizontal axis. So let's say you have, this is X. I want you to tell me how much is N and how much is P. So I want to draw the electron and hole profiles. What will they be? Okay. We can start with, let's say, holes. How will the holes look like? The profile of holes look like from the band diagram. Remember, band diagram essentially is telling us the distribution of holes, right, across the semiconductor. What is the quantity that tells us what is the distribution of holes across the semiconductor? Well, it's a distance of EF from EI, right? So essentially this quantity is the proportional to carrier concentration, isn't it? So if we, this is, I mean, just for your, just to refresh memory, EF minus EI is equal to KT ln of Na by Ni, right? This is the expression. So if you know the distance, we know what is the carrier concentration, right? In P-type. Okay. What is the carrier concentration? What is the number of holes in the N-type region? Let's do that. So let's just start with, far away from junction. This is simply going to be some Na, right? The number of dopants in the P-type region. On the other side, you're going to have, is it Nd? Well, Nd is the donor atom, so that will give you the electron concentration. The whole concentration is going to be Ni square divided by Na, right? And how are they connected? What is the profile? If you look at it closely, you see that as you move towards the junction, the distance between EF and EI is reducing and then it's flipping, right? There is a smooth variation of EF minus EI across the junction, right? So the whole concentration is going to be following the same trend. So you're going to have whole concentration which comes like this, okay, across the semiconductor, across the PN junction. What happens to the electron concentration? Well, the same story. You could simply, it could be different from, Nd could be different from Na. Let's say this is Nd, slightly lower than Na. That's the N-type region. So automatically your electrons in the P-type region are going to be slightly higher than the corresponding numbers in the N-type. Ni square divided by Nd, right? Again, the electron concentration is essentially EF minus EI, correct? This part. And as you go here, the distance is reducing. So essentially, gradually, there's a change in the electron concentration. So the concentration is going to be in this fashion. Okay. And we could also simply, denote, just give me a moment here. I'll move this out. Yeah. Right. Well, so this is going to be the axis. Okay. So this is your depletion region. If you notice, it's not exactly true, right? We said there are no free charges in the depletion region. That was the assumption we made when we started out in the last lecture, when we were trying to derive electric fields and all that. We assumed that that there are no free charges, free carriers in depletion region. But you see that by looking at the band diagram, we are realizing that it's not exactly true. By the way, these numbers are not, it looks like they are comparable, but this is not going to be comparable to this. Okay, this is going to be minority carrier concentration. So this is sort of a log plot. Okay, this will be a log scale, I would say. The way you're seeing it, this is a log scale. You can think of it. Okay, so what essentially is happening is still there is some sort of a decay, right? So if you want to exactly solve the PN junction characteristics, we need to take the total charge into account. And the total charge, we have seen this already, is going to be the charge of the hole minus, so this is the whole contribution, right? This is the whole contribution. So charge of the hole minus the acceptor ion concentration. And the electron contribution is going to be this, right? So this is the charge neutrality relationship which we have seen, okay, already. So the total charge is going to be this. So we have to solve this row instead of what we have approximated. So in the last lecture, we said that this is going to be your charge profile, right? This is going to be your positive charge, and this is going to be your negative charge, and the charge is uniform, and we made the calculations. But in reality, there is a small change, right? So this particular approximation that we make, we are not exact. If you want to take the exact charge into account, it becomes complicated analytically, and it's unnecessary also. You'll see that it's unnecessary in a moment. So essentially, we are making an approximation which we call as depletion approximation. Okay. So if you make this approximation, it is going to give you some numbers. We will see in the next lecture towards the end, I'll give you a short demo, and you will see that this is going to be almost close to the exact numbers. But yeah, we should keep that in the mind, okay? That this is an approximation that we are making, essentially assuming that depletion region is free of electrons and holes. Okay. This is not going to be true all the time, but the answer is going to be still close enough. Even our calculations by depletion approximation, you'll see that they're going to be close enough. All right, so this is about the band diagram. We want to find out what is the built-in potential. If you remember, we had given an expression which is a quadratic form, right? I mean, the quadratic expression for built-in potential. That's not a very convenient thing to actually use, right? So I'll give you a simplified expression. So for that, what we will do is, let's see, what is the built-in potential here? If you look at it, the built-in potential is defined as simply the difference in EC in the P-type region and N-type region. If you look at that, that is the built-in potential, right? So I'll say VBI is simply going to be EC in the N region minus EC in the, well, it's positive. You take it as positive, okay? Whichever, I mean, of course, P region, EC in the P region minus EC in the N region. All right. So if you want to calculate that, you could also write it as simply the difference in the EI. So I like, because EI is parallel to EC, so I can simply make it, this is EI in P region minus EI in N region, right? I need to use that something as a reference, and that reference is going to be my Fermi level, right? So I'll add and subtract Fermi level, right? So it's going to be EI P. I'll just leave it as EIP minus EF plus EF minus EI N, right? So basically in the N region, you take the EI, subtract it from EF, and P region, you do that, you get something, right? And we have already seen, remember, there's these expressions. This is going to be your phi times, sorry, Q phi P. Phi of P I introduced, right? I said essentially the distance is going to be the Fermi level. That expression is going to be KT ln of NA by NI, right? This is the first expression. Plus, the second expression is going to be, I'll put it below this. Okay, this is going to be Q times phi f n. That's going to be KT ln of ND by NI. Okay. So we see that the built-in potential is simply phi fp plus phi fn. That is going to be KT. Okay, I have to take Q also. So basically KT by Q ln of NAND divided by NI square. All right. So this is a much more useful expression, or much more useful form of a built-in potential. Okay. So you might ask, let me see, what is the typical numbers for built-in potential? Okay. So what are the typical doping? What are the typical doping? 10 power 15 or so, right? Let's take Na is equal to 10 power 15, Nd equal to 10 power 16. Let's take these numbers. Okay, centimeter, both are per centimeter cube. Okay, so what is the built-in potential? Same thing we have done multiple times. So KT ln, right? KT ln, remember we said that is going to, we are going to approximate it by 60 milli electron volts in those case, energy cases. Now divided by Q, so it's going to be 60 millivolts into log of 10 power 31 divided by 10 power 20. So this is an approximation, of course, right? So this is going to be 11, right? 11 times 60 is going to be 0.66 volts. The exact answer is going to be slightly smaller. You can compute it, okay? So this is 0.66. So what is the range over which your built-in potential can change? Well, of course, it can be zero. When it is zero, essentially you have, identical semiconductors in some way. Okay, you'll see that EF is continuous. There's no junction at all. Then it is. The moment your Ni and Nd start differing, then you have, you can calculate what is the maximum you can get built-in potential. You can understand. You can think about it from this perspective. If you want to maximize the built-in potential, you have to make this large and this also large. What is the highest EF minus EI you're going to get? For example, in a p-type semiconductor, you can move your Fermi level close to EV. In an n-type semiconductor, you can move your Fermi level close to EC. When we do that, what is the built-in potential that we're going to get? The built-in potential will be close to EG. Okay, so it turns out that VBI is always going to be less than EG. Okay, if you want to talk in terms of voltages, it's going to be EG by Q. If you say 1.1 EV, for silicon, if you take, for example, silicon is going to be 1.1 volts. For gallium arsenide, it is going to be 1.42 volts. So the band gap is going to sort of create an upper limit for your built-in potential. Okay. Also, we should remember that the doping, right, typically is basically less than 10 power 20. Okay. We don't take very, very high doping. And we have seen, in one of the first lectures, first week, where we changed the carrier doping density. As we increase the doping density, the Fermi level was approaching the either EC or EV. Okay, but the rate at which it approaches is, slowed down dramatically as you go to higher concentrations. The reason is the carrier concentrations appear in the log term. So for a couple of orders, there's going to be a small change in EF. Okay, so so we don't really go for high doping. And there are also other reasons, there are more complications, such as, we assumed that dopants, the donors and acceptors, are completely ionized so far in this course. But it turns out that if you go to high concentrations, the donors and acceptors are not fully ionized. Only some of them are ionized, and the ionization fraction reduces as you go to higher and higher concentrations. So there is no really point in, increasing the doping density beyond 10 per 20. Unless there's something very specific you want, or you want to make it into a silicide or something. Okay, and also remember the silicon doping, silicon concentration, density of silicon atoms is 5 into 10 power 22, right? And if you introduce 1 into 10 power 20 dopants, essentially we are having one dopant in about 500 or so atoms, right? So that's a lot of doping density. So you are effectively starting to change the properties of silicon itself. It's no longer doping that is just going to perturb your bands, but the entire material properties are going to change. Okay, so for those reasons, we typically don't prefer to have very high doping. All right. So, I have already done this. So this is an example from your textbook. So I would, there would be a solution also in the textbook. Please go and refer to example 7.1. And this is going to be what? So essentially, we are having two acceptor and donor concentrations are given to you. So please compute. So this is going to be, I'll simply write the solution anyway. So VBI is going to be, we know, right? The whole thing we keep repeating. Millivolts into log of 2 into 10 power 17 into 10 power 15 divided by, if you want to do exactly, here I see 2. So I'll simply put 2.25 into 10 power 10. Okay. So essentially, I'll say 2 and 2.25 are almost equal. So this is going to be simply 60 millivolts, approximately 60 millivolts into 12. That's going to be what? 12, is it right? Yeah. 0.72? Something like that, right? So just please verify it. This is not exactly 60 millivolts. I think this is going to be 59.5 millivolts or something. So there's a small change, but you would verify that anyway. Okay, so this is how you determine the built-in potentials for PN junctions. All right. So I would stop here. In the next module, we will talk about depletion, how to calculate the depletion widths and electric fields. Okay, I'll see you then.